and welcome back to the shop. Today's video, well, is going to be about heat treatment, and more than that, it's going to be mainly about quenching. But before we get into that, I'd like to say that I haven't been producing too much lately, but it has been exciting around here. Actually, I've had a little accident, and well, here's one of the bruises that I can actually show you. What's the accident? Well, unbeknown to me, I was enrolled in some gliding courses, and well, I guess I didn't do that well because my taking off was great, my flight was amazing. It's the landing that was difficult. Now, I have no video of the accident, but I do have a few pictures and I can talk you through it. So here's where I took off. This section here was the section that I flew over, and well, here's where I landed. And I can tell you, stone staircases are very hard, but nothing was broken, amazingly enough. Just a lot of cuts and bruises and contusions, I guess we could say. Now, the question that I received, the one that pushes me to produce this short video, well, it was a question that came out of left field. Now, I get a lot of questions about heat treatment, and well, we have some good videos about that, and I get a lot of questions about materials, and well, we also have a lot of good videos about that. But today's question sort of mixes it all together, and the question is, why do tool makers dunk, submerge the part that they're quenching and leave it submerged while moving it around, whereas a blacksmith dips his part twice, sometimes 3 times, to cool it down? Why the difference, seeing as both are quenching? Well, the difference has a lot to do with carbon. You may or may not know that steel isn't iron, and well, that iron isn't steel. There is, however, iron in steel, but there's no steel in iron. Iron is an element, so it is at its simplest just atoms of iron. Whereas steel is a mix. It has to at least be a mix of iron and carbon. So if we have iron and carbon mixed in accurate proportions, and we give that part a shape by forging or whatnot, well, we've produced steel. And if I take some iron, heat it up, and give it a shape by hammering, forging, or whatnot, I've produced a piece of iron. It won't change. Now, if I quench a piece of iron, since there is no carbon in it, well, it cannot be hardened. So iron is as hard as it's going to be. It can't be made harder by heat treatment. Whereas steel can be usually, or in many cases I should say, hardened by heat treatment. And what do I mean by many cases? Now, there is low, medium, and high carbon steels, whereas the iron, well, is just the iron. But don't be fooled. The iron is often in presence of carbon. When it's produced in a blast furnace, for example, well, there is carbon present in the furnace, and well, the iron can absorb a certain amount of it. And well, iron that the blacksmith would use can contain some carbon, and maybe enough to be heat treatable. Now, what I mean by that is we have 3 levels of carbon steels are divided in that way. We have low, medium, and high content carbons. So high carbon steel, medium carbon steel, and low carbon steel. As a general rule, and although it's not bing bing at the low and high, there's a line in between the two that's very accurate. No. General rule, low carbon steel cannot be hardened by heat treatment. Medium carbon steel can be hardened by heat treatment to a medium hardness. So somewhere around 40 to, let's say, 55 Rockwell C. Now, if you don't know what this is all about, and it could be the case, you may want to head back a little bit and go take a look at the series of videos that covered the heat treatment. It's probably pretty boring stuff, but it's important stuff. So, medium carbon steel can be hardened to a medium level. And while high carbon steel, often called tool steel, well, can be hardened to a high degree of hardness. We're talking here 60 to 75 Rockwell, somewhere around there, Rockwell C. Okay, great stuff. So low, medium, and high carbon steels. What does that represent? So 0 to 0.3% carbon in the mix will be considered a low carbon steel. 0.3 to somewhere around 0.6 will be a medium carbon steel. We'll say 0.55 instead of 0.6, somewhere around there. And well, let's say a 0.6 to about a 0.83. And now I'm going by memory here, but I think 0.83% of carbon in iron is the point of saturation of carbon in iron. Any more than that, and you get free carbon in the mix. So let's say from 0.6 to 0.83, we have high carbon steels. Now, what the blacksmith is using is iron. And with a lot of experience, the blacksmith can judge, maybe even without knowing exactly what's going on, chemically speaking, but can judge about the amount of carbon that he has in presence of the iron. And maybe it's just borderline a medium carbon steel, or maybe it's somewhere in the high end of the low carbon steels. And that means that he could harden it by quenching, but be careful. There's hardening in surface and there's hardening in depth. What I've just described, whether it be steel, low, medium, or high, plain carbon steels, or the iron that is mixed with carbon that the blacksmith may well use, in both cases, it is difficult to harden those materials through and through. Let's say I had a 1 inch by 1 inch block of steel, medium carbon steel, let's say plain carbon steel, just iron and carbon. Well, if I had that, I would get a hardness on the outside. I might even manage to get a 1/16 to an 1/8 of an inch of depth, but I won't be getting much more than that. And why is that? To harden a piece of steel, we need to heat it up to within its critical range of temperature. Again, in the heat treatment videos, we talk about it. And then we have to cool it down quickly. But how quickly we cool it down has a lot to do with what's in the plain carbon steel. So when all that we have is iron and carbon, well, we have to cool that down very quickly to get it to harden. So if I have a thick, massive part, when I quench a part, it cools from the outside towards the center. Now the outside will cool quite quickly, but the middle is going to take a long time to cool and it just won't harden. So plain carbon steels have that problem, and the blacksmith has that problem, and that is why they dip instead of a dunk. And we'll talk about that in a few seconds. Now, how can we get through and through hardened steels that we'll use for punches, for tools, for all kinds of things? Well, they are called alloy carbon steels. And, well, they add, where they produce these materials, different alloying elements that change the properties of the steel. Now, if you're looking for a steel that will quench readily and harden through totally through the part, that even if it is massive and thick, well, you're going to be adding elements that make the part easier to quench. Now, a 4140 alloy carbon steel is a medium carbon steel. The 41 tells me that. But it is an alloy steel that contains elements that really help the quenching. So when I quench a part of 4140, well, I can expect that it's going to get hard through and through. It doesn't have to cool down as quickly to stay in that hardened state. Okay, plain carbon steels have to cool down fast. Iron with carbon that a blacksmith may use has to cool down very fast. Why? Well, because the blacksmith's mix of iron and carbon very often only really has carbon on its outer surface. So it really has to cool down quickly if we're going to get anything that resembles a hardened part. So that is why we get the double dip. Why? Well, when the blacksmith dips and pulls out, it's generally accompanied by a push. Push is a technical term, but a push of steam. And that steam is an indication of a liquid, in this case water, going from a liquid state to a gas state. And to do that transition, well, the material water has to absorb vast amounts of energy. That means that when we dip and pull out and let the steam fly, we're actually cooling the part very quickly. If we see that the steam is starting to lower, I quickly dip it and pull it out a second time to keep that drawing of energy from the part going at its fastest rate. Now, once we've reached a certain temperature, it doesn't have to be completely cold, but anywhere under really about 1100 degrees, but we'll play it safe and say 800 degrees Fahrenheit. After that, you don't have to cool it anymore. It's hard or it's soft, but if it did harden, it's going to stay that way. Even if the part is quite hot, it's not hot enough to change that state. So that is why the blacksmith double dips. He needs or she needs to cool the part as quickly as possible because of the quantities of iron that is in the part. Now, we said that 0 to 0.3% of iron, of carbon in steel, well, is a low carbon steel, and they're generally considered to not be hardenable. However, even if I have a 0.2% carbon, so clearly in the low carbon steel zone, if I can cool it down quick enough, I will get a certain amount of hardness, but I will not get very much penetration. Is that clear? Now, why do tool makers not do that? As a general rule, the faster you cool down a part, the more deformation that part is going to suffer during that cooling process. Now, if I'm a blacksmith and I get a certain number of thousandths of an inch, let's say, deformation on the part that I'm producing, who cares? The work isn't that type of accurate. I mean, a blacksmith works very accurately. I'm always amazed at what these people can do. But it's not the same type of precision that a toolmaker would need. We have less skill, but more accurate ways of producing things. So if I want to produce a hardened punch for a punch and die, let's say, and I want that punch to be accurate within a few thousandths of an inch, well, I'm going to have to grind it after I heat treat it. We've heard all about that in our videos. But I want it to deform the less possible because I want to grind it the least possible to finish it. So I'm going to rough the part out, leaving a certain amount on it, and we saw that in our 1, 2, 3 block project videos. And then I'm going to heat treat it, and then I'm going to go to the grinding and grind it to its final, very, very accurate dimensions once it's hardened. But I do want the least amount of deformation possible. So I use an alloy carbon steel. If I have, again, I'll come back with the 4140, I could have chosen 01 steel as well, oil hardening class 1 or a tool steel. The quenching in oil actually slows down the cooling process. And that is not a problem with steels like alloy steels that are made to be hardened easily. Because even if I cool down slower than water, well, I still get a hard part. I mean, when you quench, it's either hard or it's not hard. You can't harden half. You can get better penetration, but hard or soft, that won't change. So let's say I quench and it cools down slowly in oil. Well, I will get less deformation on complex parts, plus an added bonus. The parts that the toolmaker produces often has internal angles. And well, these parts are prone to cracking. The faster it cools, the more prone to cracking tool steel will be. So if I can quench it in oil and cool it down slowly, well, that is a good thing for cracking as well. So we see there's a lot of advantages that the plain carbon steels just don't have. So that is the reason why. So why doesn't the toolmaker dunk? Well, you see this lovely face, you see these eyebrows and eyelashes, and a total lack of hair up here. But that lack of hair isn't due to a large fire or explosion, oil explosion. Now think of it. If we have examples of many projects that we've produced videos on where you see that I dunk. When I dunk a part in oil, I want to keep it dunked. Now, heat treatment oil has a flash point of somewhere around 600, 650 degrees. I forget, somewhere around there. And that means that it will spontaneously ignite at that temperature. Great. As long as I keep that temperature below that, it won't ignite. My part, let's go back to our 4140, needs to be around 1550 degrees before I dunk it in the oil. That means I'm going to get a fire. Not really. There has to be air in presence for there to be a fire. It's a rapid oxidization, basically. So if I dunk the part in oil and keep it well under the surface of the oil, the part may be very hot, but there is no oxygen in there and we will not get an explosion. Remember, I am using specialized heat treatment oils. Don't do this with any other type of oil. It is very, very dangerous. Okay, that being said, I keep it well under the surface. Now, if I, by pure lack of knowledge, and this is where terrible accidents happen, if I dunked and pulled out, like the blacksmith does, well, I would have oil on the surface of that part, and I would have a part that's around 1500 degrees or so that has oil and oxygen available. Now 1500 degrees, and you can count 6, 12, 18, is not very far from 3 times the flash point of the oil that we're using. And that means what? That means poof, that means major flames, that means a big, big problem. So we never want to pull our part out of the oil. And we're using the oil because our parts have to maintain accuracy, and the high carbon steels, even the medium carbon steels, are prone to cracking. The blacksmith doesn't have these problems. His main preoccupation is to cool that part down as quickly as possible. So dunk, pull out, steam, amounts of energy coming out of the part as quickly as possible. That's not what tool makers do. Now, the last thing that I often get questions about the quenching itself, well, is why once we quench do we move around? Now, when you dunk your part in the large quantity, you don't do this in just a little bit. You need a big barrel or a large container. We're talking several gallons here. When we dunk it in there to quench the part, oftentimes you'll see me moving in a slow figure 8 movement so that the part moves around in the oil. I never pull it out until it's cool enough not to ignite, so somewhere below 600 degrees, but I will move it around. Now, why is that? You'll see if you dunk it in, there's going to be a certain amount of gas. That oil is going to turn to gas, liquid to gas, and it's going to envelope the part, envelop the part. And well, that actually creates a barrier here between the cool oil. We're going to have a liquid to solid transfer of heat. And that is problematic, especially if I dunk the part a little at an angle and one part gets more in the liquid faster or has less accumulation of gases at its surface. There we have deformation because it's not even. So if I dunk as straight as possible, and then I move slowly in a figure 8, well, I'm ensuring that the fresh oil comes in contact with all the surfaces of the part as evenly as possible. So there you go. I hope that this has cleared up some of the mysteries surrounding quenching. Remember, quenching in water is never dangerous. I mean, you can't start a fire in a bucket of water. We agree. But quenching in oil is very dangerous. Do it outside if you don't have a proper quenching area that is conceived for that. Do it outside. Use only a quenching oil, and do it only if you really understand what's going on. Wear full face protection and full body protection when you do it, because if that fire starts, it could get ugly very, very quickly. So, until we meet again, have fun. Be safe. I hope you managed to stay awake for the whole video. And well, happy machining.
So all I ever wanted was a little monkey from you.